I welcome all for the first session of Engineering Mathematics 4 Model 1. So let me introduce myself. So my name is Dr. A. Srinivasa, Professor and Head, Department of Mathematics, MIT, Mysore. In this session, today we are going to discuss the numerical solution of ordinary differential equation of first order and first degree. So I'll take some introduction regarding about numerical solution. So in the previous semester we already solved so many differential equation problems by analytical method. So they are getting a closed form solution, that is expressing a y in terms of a finite number of elementary function of x. However, a majority of differential equation appearing in physical problems cannot be solved numerically. Thus it becomes imperative to discuss the solution by numerical methods. So numerical method of initial value problem. So let us consider the first order and first degree differential equation of the form dy by dx equal to f of x comma y with a initial condition y of x naught equal to y naught. So that is y equal to y naught and x equal to x naught, called as an initial value problem. So these initial value problem can be solved by the following methods. First one, it is Taylor series method, modified Euler's method, Runge-Kutta method of fourth order, Millen's predictor corrector method, Adam-Bashforth predictor corrector method. In this session, we are discuss how to solve the initial value problems by Taylor series method. So I have to see the initial value problems. The Taylor series expansion of a function y of x in powers of x minus x naught can be defined as follows. That is y of x equal to x minus x naught by 1 factorial y1 of x naught plus x minus x naught whole square by 2 factorial y2 of x naught plus x minus x naught whole square by 3 factorial, then y3 of x naught plus x minus x naught whole power 4 by 4 factorial into y4 x naught. Here y1, y2, y3 and y4, they are all a derivative. y1 is the first order derivative, then y2 is the second order derivative, y3 is third order derivative and y4 is fourth order, and so on at a given point x naught comma y naught. Today we are going to solve some problems by using Taylor series method. So the first problem, so we are going to see some worked example. Using Taylor series method, find the value of y at x equal to 0.1 and x equal to 0.2 for the initial value problem, that is dy by dx equal to 3x plus y square with the initial condition y of 0 equal to 1. So these are the problem I will solve on board. So taking on the first problem, so dy by dx should be equal to 3x plus y square with the initial condition y of 0 equal to 1. So first let me explain the Taylor series expansion. Taylor's series expansion for y of x at point x naught is, to use this formula, y of x equal to y naught plus x minus x naught by 1 factorial into y dash of x naught, that is y1, plus x minus x naught whole square by 2 factorial into y2 of x naught plus x minus x naught whole power 3 by 3 factorial y3 of x naught plus then x minus x naught 4 factorial then y4 of x naught. up to some infinite values is there now. So here in your syllabus they mention how to express the Taylor series expansion up to 4 degree, and also given this is the solution we are taking now here. Y of 0 equal to 1, you should have to compare with y of x naught equal to y naught. The comparison of these two, your x naught becomes 0 and y naught, that is also become 1. Then your Taylor series becomes y of x should be equal to, in place of x naught you are taking 0, y naught plus x by 1 factorial y1 x naught at the point 0 plus x square by 2 factorial, again second order derivative at the point 0 plus x power 3 by 3 factorial y3 of 0 plus x power 4. So we can express the Taylor series up to 4th degree terms. Now call this as equation star. Then your derivative dy by dx we are simply calling as y1, that should be equal to 3x plus y square. Now at the point y1 of x naught is equal to 0, it should be equal to 3x naught plus y naught square. In place of x naught you put 0, in place of y naught you put 1. These values become 3 into 1 plus 3 into 0 plus y naught is 1 square. This value become 3, 0 plus 1, 1. So that will give y1 value. Your y1 at x naught equal to 0, this value is 1. And similarly next, differentiate y1 with respect to x, then it becomes y2. The y1 is 3x plus y square. The differentiation of this become 3, x is 1 plus 2y into y1. Again at the point y2 of 0, it should be equal to 3 plus 2 into, this value is y naught, the y naught value is 1, then again y1 value is 1, then it become 3 plus 2 become y2. So that will give the y2 value is 5. Then again you differentiate y2 with respect to x, it will give y3. So I will write on here now. Now again differentiate y2 with respect to x, then we get y3, it should be equal to, differentiation of 3 becomes 0 plus, you have to apply product rule here, 2 into first into second y into y2 plus second into first, already y1 is there, now differentiation of y, it become y1, y1 into y1 it's become y square. Again at the point x naught is 0, y3 is 0 plus 2 into your y naught is 1, then y2 value is 5 plus again y1 value 1 square should be equal to 2 into 5 plus 1, 6, this become 12. So y3 value is 12. Again of the 4th order degree, again differentiate y y3 with respect to x. Your y3 become y4 should be equal to, so again 2 times differentiation of 0 again 0. I have to apply a product rule, first into second plus second into first, y2 into y1 plus, now differentiation of y1 square is 2y1 into y2. Then y4 is equal to 2 times of the addition of these two, it will give 3 times of y1 into y2. Again y4 at the point x naught equal to 0 should be equal to 2 into y naught value 1, your y3 value is 12 plus 3 into, again y1 value is 1, then y2 value is 5. It should be equal to 2 times of 12 plus 15, 2 into 27, this value become 54. Now after find outing the values of y1, y2, y3 and y4, substitute all this equation in star. So that is y of x, your Taylor series become the equation star becomes y naught, the value of y naught is 1 plus x by 1 factorial into y1 of 0 is 1 plus x square by 2 factorial into y2 is 5 plus then x power 3 by 3 factorial into 12 plus x power 4 by 4 factorial into 54. So this is the required Taylor series expansion up to the 4-degree term. Then you have to put x equal to 0.1, we get the corresponding value of y 1 plus, this is the Taylor series expansion up to 4-degree term. This is 0.1 by 1 factorial is 1 into 1 plus 0.1 whole square by 2 factorial into 5, the 2 factorial value is 2 into 5 plus 0.1 whole power 3 by 3 factorial value 6 into 12 plus 0.1 whole power 4 by 24, the 4 factorial value is 54. By using calculator and simplification of this, we get the value for 1.12722. And similarly, again put x equal to 0.2, we get y of 0.2. That means you have to replace in the place of x as a 0.2. We will get 1 plus 0.2 by 1 factorial into 1 plus 0.2 whole square by 2 factorial into 5 plus 0.2 whole power 3 by 3 factorial into 12 plus 0.2 whole power 4 by 4 factorial into 54. Again by using calculator, the simplification of this, we get the value of 1.3196. So this is the first example to understand the Taylor series expansion. And similarly, we move to one more problem to understand this concept. I can work at example number 2. Again, solve by using Taylor series method. Find the value of y at x equal to 0.1 and 0.2 for the initial value problem. So this one initial value problem, that is dy by dx should be equal to x square y minus 1 with y of 0 equal to 1. Again same, I have to expand the Taylor series expansion up to 4-degree term. First I have to write down the formula. Taylor series expansion, Taylor series expansion up to 4-degree term is, that is y of x equal to y naught plus x minus x naught by 1 factorial y1 of x naught plus x minus x naught whole square by 2 factorial y2 of x naught plus x minus x naught y3 of x naught plus then x minus x naught 4 factorial, that is y4 of x naught. So in your syllabus they mention only how to extract the derivative for up to 4th order. So given, so again use the initial condition y of 0 equal to 1. Now compare this y of x naught equal to y naught. Again from this problem x naught equal to 0 and y naught equal to 1. These two are the initial condition. Then after that your Taylor series becomes, Taylor series becomes at the point at x naught equal to 0, that is y of x equal to y naught plus, in place of x naught you put 0, x by 1 factorial y1 of 0 plus x square by 2 factorial y2 of 0 plus x power 3 by 3 factorial y3 of 0 plus x power 4 by 4 factorial, that is y power of 0. Now call this as equation number star. Again you have to follow the same procedure what we did in the previous problem. So you can assume the derivative dy by dx as an y1 then should be equal to x square y minus 1. Now again you put the point y1 of 0, that means x naught equal to 0. At a point x naught equal to 0, your x naught value is 0. y1 of 0, it should be becomes x naught square y naught minus 1, that is x naught square y naught minus 1 should be equal to, the value of x naught is 0 square, 1 minus 1, this totally become 0 minus 1, this value is minus 1. That gives the y1 value at the point x naught is minus 1. Then again differentiate this one, differentiate y1 with respect to x. If we differentiate with respect to x, we get y2. The differentiation this, we have to apply here product rule. First into second plus second into first. The differentiation of 1 become 0. Now again you have to put the point at x naught equal to 0. y2 this should be equal to, the value x become x naught square, 0 square into 1 plus the value of y naught is 1, 2 into the value of x naught, again 0. So 0 plus 0, this value becomes 0. That means your y2 value will become 0. Then again differentiate y2 with respect to x. It will give third order derivative. Then y3 should be equal to, again apply the product rule here, first into second, x square first into second plus again second into differentiation of first one, y1 into 2x plus again I have to apply product rule, take 2 as a constant term, first into second plus second into first. Differentiation of x is 1. Now to simplification of this, x square y2 plus 2x y1 plus 2x y1 plus 2y. Again y3 equal to x square y2 plus the addition of these two, 4x y1 plus 2y. Again substitute the point at x naught equal to 0. y3 at x naught equal to 0. This value will gives, this is 0 because x naught 0 into multiplication of anything is 0 plus. Again this value is also 0 because x naught value 0 plus 2 into y become y naught, this value is 1, get 2. So finally y3 of 0, this value become 2. Then again I'm going to find out the fourth derivative. Differentiate with respect y3 with respect to x. Now I'm going to differentiation of this one with respect to x. This become y4. Again I have to product rule is there now. Apply the product rule. First into second plus second into first. Again I have to apply the product rule here. 4 times of first into second plus first into second, then second into first, y1 plus 2y1. Now simplification of this, x square y3 plus 2x y2 plus 4x y2 plus 4y1 plus 2y1. Again at y4 equal to y4 of 0, that means x naught value 0. This value 0 because x is there now, 0, 0 plus 4 into 1 y1, the value of y1 is minus 1. 4 into minus 1 plus 2 into minus 1. So finally we have minus 4 minus 2. This value becomes minus 6. That means y4 value, y4 of 0, this value become minus 6. Now substitute all these values, y1, y2, then y3, then y4 in the Taylor series expansion, that is equation star. Then equation reduced to in this form, then equation star becomes, that is y of x, it should be equal to y naught value as usual 1 plus x by 1 factorial into minus 1 plus x square by 2 factorial into the y2 value 0 plus then again x power 3 by 3 factorial into 2 plus then x power 4 by 4 factorial into minus 6. So this is the required Fourier series. This is the required Taylor series expansion up to the fourth order. Then again you have to find out the value of x equal to 0.1 and x equal to 0.2. Then again put x equal to 0.1. Then y of 0.1 in your Taylor series expansion 1 plus 0.1 by 1 factorial into minus 1 plus 0.1 whole square, this is become completely 0, plus 0.1 whole power 3 by 3 factorial is 6 into 2 minus x power, again 0.1 whole power 4 by 24 into 6. Using your calculator, it gives some values. 0.90031. Then again put x equal to 0.2 again in your Taylor series expansion, that is 0.2. 1 plus, in place of x you put 2, 1 factorial value is 1, this term 0, 0.2, 3 by 6 into 2 plus 0.1 whole power 4 by 24 into 6. Again using this we get 0.8023. So this is the way we can solve the initial value problems by Taylor series method. So let me know one more problems to understand this Taylor series expansion again. So it is a very important problem in examination point of view also. Example number 3. Solve again the same initial value problems. Dy by dx minus 2y equal to 3 e power x at a point y of 0 equal to 0. And take down the solution of this. Again Taylor series expansion, up to 4th degree is, to use this formula, y of x equal to y naught plus x minus x naught 1 factorial y1 of x naught plus x by x naught whole square by 2 factorial y2 of x naught plus x minus x naught 3 factorial y3 of x naught plus 4 factorial then y4 of x naught. Now call this as equation star now here onwards. Finally you substitute all the values of x naught and corresponding y naught after find outing this. And given data y of 0 it should be equal to 0. This is compared with y of x naught equal to y naught. Now comparison of these two, we get x naught value is 0 and corresponding y naught value is 0. And your first order derivative, you should have to write down the derivative in this form, 3 into e power x. It's dy by dx. You simply transfer 2y that side, 2y plus 3 into e power x. And simply this is y1, 2y, 3 into e power x. Now y1 at the point x naught, the x naught is 0. Now putting this is y naught plus 3 into e power x naught. y1 of 0, 2 into the value of y naught is 0 plus 3 into e power 0. 0 plus 3, we get y1 of 0 is 3. Then y2, that means I have to differentiate y1 with respect to x. Then we get y2. The differentiation of 2y, this become 2y1. 3 is constant. Differentiation of exponential function is again e power x. At the point y2 of 0 should be equal to 2 into y1 value is 3 plus 3 into e power 0. 6 plus 3, this become 9. Then again differentiate y2 with respect to x. It becomes y3. So I will write down here now. This y3 should be equal to the differentiation of this 2 into y2 plus 3 into e power x. Now again you substitute the point y3 at x not equal to 0. 2 into the value of y2 is 9 plus 3 into e power 0. That is an 18 plus 3, we have 21. That is y3 of 0. Then again differentiate with respect to x, y3, then it becomes y4. This is 2 into y3 plus 3 into e power x. Differentiation of e power x, again e power x. y4 at 0 should be equal to 2 into y3 is, this is 21, 3 into e power 0. The e power 0 value is 1, get 45. This is y4 of 0 is 45. Now again the same thing. So after finding out all these things, y1, y2, y3 and y4, substitute in equation star with their initial conditions. The initial conditions is again x naught 0, y naught 0, substitute in equation star. So I will write down here now. Equation star becomes equation star becomes, that is your Taylor series expansion, y of x equal to, your y naught value is 0 plus x minus x naught, that is x by 1 factorial into the y1 value is 3 plus again x square by 2 factorial into y2 is 9 plus x power 3 by 3 factorial into 21 plus x power 4 by 4 factorial into 45. So this is the required Taylor series expansion up to 4th degree term. After finding your Taylor series expansion, they asked you find out the value of x1 and x values at point 1 and point 2. That means just simply giving x equal to point 1 here, the corresponding y of point 1 value will be obtained. It comes like that, point 1 by 1 factorial is 1 into 3 plus point 1 whole square by 2 factorial into 9 plus point 1 whole power 3 by 6 into 21 plus point 1 whole power 4 by 24 into 45. And again you are using your calculator, it will give the corresponding values of point 1. So I think you got 0.34869, 0.34869, and again put x equal to 0.2. It will give y of 0.2. Y of 0.2 value is again 0.2, 1 factorial into 3, 0.2 whole square by 2 factorial into 9, the 2 factor value is 2, plus 0.2 whole power 3 by 6 into 21, again 0.2 whole power 4 by 24 into 45. Again using your calculator to get the solution of this problem, we'll get 0.81100. So again we are going to one more problem for the evaluation of this. The next problem, it is 4th one. Again solve the initial value problem. Dy by dx equal to xy plus 1 at the initial value, y of 0 equal to 1. Again they ask for up to 4 degree term. Again you start with the Taylor series expansion and the solution. Taylor's series expansion, y of x about a point x naught, y naught plus x minus x naught, 1 factorial, y1 of x naught plus x minus x naught whole square by 2 factorial, y2 of x naught plus x minus x naught 3 factorial plus again this call this as equation star. So using the initial condition again, so given y of 0 equal to 1, again compare with this, y of x naught should be equal to y naught. Your x naught value is 0, comparison of these two and comparison of these two. Then your y naught, the corresponding value is 1. As usual, again you take the derivative and have to differentiate again and again. We get the up to 4th order degree terms. And simply can take dy by dx equal to y1 should be equal to xy plus 1. That means at a point x0, y1 of 0, you are at a point x0 is 0, this x become x0, x0 value is 0, the corresponding y0 1 plus 1, it will gives y1 of 0 is 1. Again differentiate y1 with respect to x. This become y1 becomes y2. Now to use first into second, then second into first. Product will apply here, first into second plus second into first. 1 as usual they become 0. Again y2 at the point x0 equal to 0. x0 value is 0. The y1 is 1 plus y0 value is 1. And totally we have 0 plus 1, this value is y1. Then again I have to differentiate y2. Differentiate y2 with respect to x. Then your y2 it becomes y3. Again I have to apply the product rule. First into second plus second into first, y becomes y1. Now addition of these two, x y2 plus 2 into y1. Then again y3 at the point x0 is 0, it becomes like that. This becomes 0 because x0 value 0 into y2. The y2 value is 1 plus 2 into your y1 value. y1 value is 1. Then y3 of 0. This become 0 plus 2. This become 2. Then again differentiate y3 with respect to x, it will gives y4. Apply the product rule. First into second plus second into first plus 2y2. Then again at the point x0 equal to 0, this value becomes 0 plus the y2 value is 2, then again plus 2 into 2, then y4 of 0, 2 plus 4, this become 6. That is y4 of 0 is 6. Again after find outing all this one, y1, y2, y3, y4 along with this initial condition are to substitute in the equation star. Now substitute all these in equation star, it will gives like that. I am writing here now. Equation star becomes y of x equal to your y0 value. The y0 value is 1 plus x0 is 0, x by 1 factorial. The y1 of this is 1 plus x square by 2 factorial into, again y2 value is 1 plus then x power 3 by 3 factorial into 2 plus x power 4 by 4 factorial into 6. So this is the required Taylor series expansion up to 4 degree term. Again as usual, putting x equal to 0.1, it gives the corresponding values of 0.1, and again putting x equal to 0.2, that will gives y of 0.2 value. This become 1 plus again 0.1 by 1 factorial plus 1 factorial value is 1, 0.1 whole square by 2 factorial, that value is 2 into 1 plus x power 3 by 3 factorial is 6, 2 plus x power 4 by 24 into 6. So again, using your calculator, it will gives the value in this form. .1053. Again, you have to substitute the same in place of 0.1. 0.1 whole power 3 by 6 into 2, again 0.1 whole power 4 by 24 into 6, that will give 1.1053. Similarly, in place of x you putting 0.2, that will also gives the value of y of 0.2. And you need one more problem is there. Now I'm going to solve one more problem also. Okay, let me summarize the Taylor series method. So again, first you have to define the Taylor series expansion only for the initial value problems with y of x as a condition at a point x naught. It will gives y naught plus x minus x naught by 1 factorial y1 of x naught and x minus x naught whole square by 2 factorial at y2, and similarly and so on. So this is the way we can solve the numerical method for differential equations by Taylor series method.